Hello student, welcome to the first lecture of digital electronics. Okay, so today we will talk about number system and data representation in digital logic. So first let me know if my voice is clear or not, if I am audible, if the screen is visible or not. Please let me know in the comment section. So anyone please reply in the chat. Okay. Till that time, let's discuss why this crash course is important. Especially for if we talk about digital logic, only 4 to 5 marks comes from this subject. So students get aspirant don't like to waste too much time on subject like this. So for them, this crash course is very much important because you will get to know most important topics from this subject within 5 lectures. I can assure you there is no prerequisite for this course. If you attend all these lectures of Get Crash Course, or at least from this topic, you will answer everything. Any question comes from this topic, you will able to answer. Okay, that is my responsibility. Okay. So any confusion, any doubt in between the session, you can comment it. Okay. So I am active in the comment section. So you can let me know if you have any confusion. Okay, fine. Thank you for the response. Okay. So uh, today we will talk about number system and data representation. Okay. So this is I think one of the most easiest topic in digital logic, but question also may get tricky because it is gate exam. So first, let's start with some basic thing. Possibly you already know all this, but still I will assume that you are learning from it from basics. Okay. So in the number system we generally use, we say numbers 0 to 9. That is called decimal number system. That is we take use in general in our real life. Okay. But in computer, they use only zeros and ones. That is called binary number system. And there are various types of number system you can like think about octal, hexadecimal, and there can be any base of number system. Base can be anything. Okay. So these two are more important that we use in our day-to-day life. Also hexadecimal that we use in our memory. Okay. So what is the actual range of decimal? That is we use 0 to 9. In binary, we use 0 to 1, 0 and 1. There is only two numbers. So in decimal, we have 10 number. That is also called radix or base. That is how many unique digits are present in that number system. In binary, the base is 2. Okay. Some example of decimal number system, that is most easy one, that is you can write anything 284 base 10. That is decimal number system. In binary you can write any number like this. So we represent the base here in the bottom. Okay. Then comes octal, where we use 0 to 7. Okay. So there is only 8 numbers in octal, so we say the base is of 8. And so you can write any number like 716, but you cannot include 8, isn't it? Because 8 is not in the number, in the digit. So this is of base 8. So one property you can see, this number like here is greater than all of the number present here. Okay. Then comes hexadecimal, where your base is 16. But how you will get 16 unique digits? Because you have 0 to 9, which has 10 digits. So that's why we will include A to F also. Okay. So A to F, which comes with more 6 digits. So in total there is 16 digits you will have. So that is your base is 16, also called age. Also called age. Number you can write A1, F, be base 8 or 16, anything. Okay. In the same way, base 4 will have 0 to 3. Okay. The base will be 4, and the number, any number you can think of, 3, 1, 0, and not 4. You cannot include 4 here. So let's see, 3100 base 4. This is a basic thing about a number system. Okay. So then look at some conversion. Let's look at some conversions like decimal to other. Okay. I'm not talking about decimal to any particular number system. I am taking in general that you can, using this method, you can convert decimal number to any other number. Okay, any other base. For example, here you are given a decimal number 198.25. I want to convert it into a base 2 number. How we can do it? It can be any number. I will let you know how you can generalize this process. So the number is given 198.25. First, what you have to do, you, with each digit you have to multiply. So multiply is done when you convert other to decimal. Here we are doing decimal to other, so we will not multiply, we will do division. Okay, we will do division here. So there is some digit that comes before point, floating point, and there are some digit which comes after floating point. The digit comes before floating point, we will divide it by the radix to be converted. So 198 will be divided by 2 because we are converting it into 2 or 2 base system. Okay. So if we divide it, what we are getting here, that is 9 and 8. So what is the remainder you got? Your remainder is 0. So again do division by 2 until you get 1 or 0. Okay, generally you will get 1 at last. So 4, and you have 9. Here is also your remainder is 0. Again use 2 and 24, and your remainder is 1 because this was the odd number. Again divided by 2, keep dividing this, you will get 0, and dividing it by 2 you will get 6 with remainder 0. Again divide it, you will get 3 with remainder 0. At last divided by 2 you will get result 1 with remainder 1. So when you will write the number, you will write it bottom to top. So your number is 1100010. Is it complete? No, because there are some more digit that comes after point. Huh? So to do that, write down the digit that is comes after floating point, that is 0.25, and multiply it with the same radix from to which you will convert. Okay, here it is 2. So what is the result? 0.5. 0.25 into 2, that is 0.5. Take this digit as your answer. Now again do multiplication with the rest of the after all the digit that comes after floating point. It is zero point 0.5 into 2, that is equals to 1.0. When you got 0 after point, just stop. What is your result? Here you will see your result from top to bottom. So that is important. So when you convert it into base 2, if it is before floating point, you are taking bottom to top. Otherwise, if it is comes after floating point, you will take top to bottom. Okay, is the process is totally clear to all? it is clear to all, okay, fine. In that case, please let me know the answer of this conversion. So here it will be, the process will be same. You will keep divide it by 8 and multiply it with 8. Okay. So one, is there anything wrong? No, I think it is okay. Fine. So let me know the answer of this one. Till that time I am also doing here. So we will match our answer. Okay. So 185 dividing by 8. So first will be, we will divide 8 to the 16, 225, and remainder is 1. So okay. Again 8 to 16, the remainder is 7. Yes. So the number is 271 and point. You will get this have to be multiplied with 8, which will result 2. That is base 8. This is the answer, and this is another answer. So this is the process of converting a decimal number to other number. Okay. Now let's convert any other base to decimal. So for example, we are given a binary number that we have to convert in base 10. Okay. So let's do it. First, let's write down the number 101,000,000.11. So the process is just multiply. Now there we are dividing with this base. Okay, here we will multiply using this base. So multiply using 2 plus multiply. Now there will be again some power of 2. So we are going to talk about this. Into 2 into 2 into 2. Okay, sorry, there is a point, and yeah, there is a point into 2. So when you see that floating point, before that all the number will be marked from 0 to the base you will go. Okay, how much you can go, like 0, 1, 2, 3, 4, 5. Okay, and after this point you will start from -1 and you go to some x. You will go to some x, let's say -1 and -2. Okay, so this is zero term, don't need to calculate also, this is zero term, so you can simply discard those, and otherwise it is 32 plus 8. Okay, and here it is coming 0.5 plus 0.25, which results 40.75. That is your answer. Okay, this is a base 10 number, that is conversion from this number to this. Okay, is this process also clear? How to convert any other base to decimal base. So if there is any other r, you will change the process. You will write r instead of 2, and the power system will be same. Okay, now if you are given any two base like p and you have to convert it into q, you can go p to 10 base and 10 to q base. Okay, because we are now know how to convert any base to 10 base and 10 base to any base. Why we are taking 10 base as this like this? Because generally we do multiplication and division in our general process that we assume our number system is in base 10. That's why we are taking this. Okay. Now we will also see some conversion directly from binary to octal or hexadecimal, because that is little bit easier. You don't need to go to like this long process. You can very easily get that. So let me write this is easier one. 110 1001 point 11011. Again, first look at the floating point. Okay, and from floating point, now let's say we want to convert it into octal. We are doing for octal. Okay. Okay, so first, starting from this point, we will group it with 3 digit. Why 3 digit? Because octal has base 8 and binary has base 2, and octal base 8 equals to 2 cube. That's why 3. Okay, we will group of 3. Take group of 3, and there is no 3 more digits, so just append 0. Okay, because this remains the that keeps the value intact. Okay, so after point also take 3 digits. Take 3 digits. If there is missing zeros, like missing numbers, so add zeros. Now convert each 3 group to a octal number, or you can say decimal number that will be maximum 7. That is the condition of octal also, because 3 digit, using 3 digit is the maximum number you can get is 7. So this 1 5 1 point uh, yeah 6 6. So your number is 151.66 base 8. Okay, the same way you can convert it into hexadecimal. Just take 4 groups, 4 digit groups for hexadecimal. So let me do it quickly. Okay, if you have any confusion, you can comment it. Okay, so take this 4, take this 4. There is no digit, add zeros. Take this 4 digit and also last. Okay, so now convert it digit by digit. This is 6 and this is 9. This is 13, which will be again converted to some ABC form, like 10 is A, 11 is B, 12 is C, 13 is D, and 14 is E. I think you will get your number here. So you are getting 13, which is D, and 8. Okay, this is your hexadecimal number. So if it is clear, so let's go to the next conversion and last conversion, that is hexadecimal or octal to binary. The process is simply same. That is, you have A, B, C, D, so base 8. You want to convert it into a base 2 number. Just convert each digit into a 4-bit binary. Each digit of hexadecimal number will be converted to 4-digit binary number. So A is 10. So take 1010. B. B is 11. So take 1011. C is 12. Take 1100. D is 13. So take 1101. That is your binary number. So the same concept can be also applied to convert any R based number to r to the power base x number. Okay, if you have a number that is base r and you want to convert in r to the power x or any r to the power x base number to r, just take group of x. That will do your work the same way as we are doing in binary. Okay, so now let's solve some numericals. Okay, so we will also learn many new concepts through numericals also. Okay, so we have also get previous year question along with that some extra design question for covering some more concepts. So first look at this question. What is the number of ones present in the decimal number in binary form of the decimal number? So this is given a decimal number. Okay, this is a decimal number you are given. You have to convert this decimal number into binary number and you have to count number of one present there. Okay, so it is like clear that you cannot do it directly in the conventional process because the number is too big. So you have to apply little bit trick. You have to rewrite this number in some form like 4 into, instead of 4096, just find, you can identify this is a 2 to the power number, this is also same, this is also same. Okay, so you just find out which power is this. It is, 2 to the power 10 is 1024 and multiplied by 4 is this, like 2 to the power 12. So 2 to the power 12 plus 9 into 2 to the power 8 plus 7 into 2 to the power 4 plus 5 into, you can write it as 2 to the power 0. Now you can see like 2 to the power 4 also can be written as 16 and this number also can be written in the 16 power. Okay, so let's rewrite this. 2 to the power 4 power 3, 2 to the power 4 power 2 plus 7 into 2 to the power 4 plus 5 into 2 to the power 0, which also results as 4 into 16 cube plus 9 into 16 square plus 7 into 16 plus 5 into 16 to the power 0 also same, that is also 2 to the power 0. Okay, so now you can see this is a decimal number. Okay, but this decimal number is represented in a form which can be easily converted to a hexadecimal number, because in hexadecimal number we write like this 16 to the power 0, 1, 2 and 3. So we can directly write this number as 4975 base hexadecimal, that is h. Okay, so when you have a hexadecimal number, that is very easy to convert in binary. It may not be directly that much easy from here, but it is very easy to convert it into binary from hexadecimal. So what is the process? Just take each digit, convert it into a 4-digit binary number. So it is 0100. For 9, it is 1001. For 70111. For 5, it is 0101. That is base 2. Okay, till that time it was base 10. Now count number of ones. 1, 2, 3, 4, 5, 6, 7, 8. Total 8 ones are present. Okay, is it clear? Yeah, very good, very good. So yeah, keep replying, keep also start solving by your own. Okay, so if it is clear to all, okay, it's a hexadecimal number directly. So we haven't took it directly. We have also discarded some terms. That is the process. So okay. So to explain this, let me take a simple number that is one a. Let's not go to a for now. Let's say 9 8 base h number. Okay. To convert it, now this number is equivalent to the decimal number 9 into 16 to the power 1 plus 8 into 16 to the power 0, isn't it? So these two numbers are equivalent. We say these two are equivalent. So in the same way, if you take backward process, if some decimal number is written like this, that you can say as a in hexadecimal form, that is 9 and 8, 9 8 base h. So that is the process I have applied here. Is it clear now? Okay, fine. So okay, let's solve this. This is another interesting question. Okay, so every question has some changes. It's not totally like equal. So some modification you will get here. You can see there is a minus. There is some minus sign. So how you will handle this? Okay. So let's solve this. Okay. And you also try. If you got the answer, then let me know in the comment section. So first, I know that I cannot convert it directly into decimal and then to binary. This will be a huge process. Like this cannot be done in less time, so it will require some more time. So, so what I will do, I will first write it into 16 power. That is 16 cube minus 7 into 16 square plus 8 into 16 minus 2 into 16 to the power 0. Now what you can do here is that this minus is creating problem na. So take common, that is 5 into 16 cube plus 8 into 16 1. So take these two digit together, minus, take minus as common and write 7 into 16 square plus 2 into 16 to the power 0. Okay. Now see, now you can convert this into hexadecimal independently. You can convert this number into hexadecimal independently. Okay. There is no relation between them. So just write it 5080 in hexadecimal minus it is in hexa, and here it is 702 in hexadecimal. Okay, and now you can do the minus. So if you are comfortable doing negation in hexadecimal, that's okay. If you are more comfortable in binary, then again you convert it into binary. That is a easy process. You will convert it and then do the minus. Okay, then do the subtraction. So if you do subtraction here, you will have less digit. So it will be better for you. Okay. So how you can do minus? Now don't take this 0 as 10 because we are doing hexadecimal subtraction. So if this number is lesser, take 6 but borrow 16 from here. Okay. In decimal, in decimal we borrow 10. Here we will borrow 16. So borrowing 16 we get what? 14. 14 means E. Okay. So when you borrow 16 from here, what generally happens? You are negating 1 from 8. Isn't it? You are borrowing from 8, 16. You are borrowing 16 from 8. So you will negate 1. The same process we apply in decimal. Okay, so 7. Again, you have to borrow 4 from here. So we write it 4. And you can write it here. That is 16 minus 7. 6 and 7. That is 9. So your number is 497E. Okay. Now you can convert it independently. 10 0 1 0 0 1 0 0 1 and 0 1 1 1, and for E that is 0 1 1 1 0. So how many ones you have? 1 2 3 4 5 6 7 8 9. 9 ones you have. Okay. Yes. So you are liking this type of question? Possibly, I what I can remember is this is not from Get previous year. Okay. But I cannot remember it, like possibly it is not Get previous year, but this is a good question. No? Okay. So let's go to the next question. What is the base of the number system the equation holds true? So that the equation holds true is, so there is some base of these numbers. These are not decimal normal numbers. In decimal, if you divide this, you will not get this answer. Okay. So this is some base number you are given, um, and you have to identify the base. That is your what you have to find. What is the value of r? Okay. Okay. So let's for do it. First, let's. If you don't like this division sign, I also don't like this. So let's convert it into multiplication sign. 13.1 into r into 20 base r. Okay. Now let's convert the number in binary. So we know how to convert other to binary. Sorry, not binary to decimal, because that will be easy here for us to calculation. So convert it into decimal. That is 3r square plus r plus 2. Now this number is converted like this: r base 2 with 3, r base 1 with 1, r base 0, r power 0 with 2. Okay. And here also r plus 3 plus r to the power minus 1, na? So which is 1 by r into 2r plus 0. There is 0, so you don't need to write this. So that is 3r square plus r plus 2 equals to 2r square plus 6r plus 2. So 2 cancels out, and you have r square minus 5r, which is equals to 0, which results r equals to 0 or 5. Now it is clear that r cannot be 0, because if r should be greater than all of these numbers, so r is surely 5. So our answer is r equals to 5. This is our answer. Okay. So anyone having any doubt in this question? Anyone? Okay. Okay, fine. So okay. So this is another question, that is you have a equation and you have to, where x and y are unknown, the number of possible solutions. Now look at the question. Okay. This is again some different one. So you have to find the number of possibility, like what can be the value of x, y, the number of possible solution of x and y. Okay. So we will forward in the same way, and we will see what are the possible values for x and y. Now one thing you know, using this you will get a equation, have a equation where there will be two variable x and y. So using one equation you cannot find the value of two variables. Okay, so you can find possible solutions. More than one solution will be there. That's why the question is given number of possible solution, not the solution, because the unique solution may not be exist. Okay. So let's convert it 4x plus 8, and here it is also 8y plus 3. Is it okay? Okay. Um, so 4x minus 8y plus 5 equals to 0. Okay. Now, am I writing it correct? Okay, I'm sorry. So there is some mistake in the question. The question was supposed to be 43. I'm mistakenly written it as 48. Okay. So 3 gets cancelled out, and then you have 4x equals to 8y. So 4 it is 2y, x equals to 2y. Now find the possible values. Okay. Now, what can be the possible values of x? Now you know x is the base of 43. So x must be greater than 4. Okay. And y have base of 8. So y must be less than 8. Okay. Strictly less than. So let's put x equals to 5. No, let's put values of y. Okay. Y equals to 7. In that case, x equals to maybe 14, which is okay. When y equals to 6, x equals to 12, y equals to 5, um, x equals to 10. Like this, you can go uh, how much? You can go till x equals to 3, where sorry, y equals to 3, where x equals to 6. Okay, x equals to 6. That is allowed. But then you cannot go to y equals to 2, because in that case you will get your x as uh, 4, but x should be greater than 4. So this is not allowed. The possible solution are these. How many possible solution? 3, 4, 5, 6, 7, and there are pairs. So 3, 4, 5. There is 5 possible solutions. Okay. Okay. Is it clear? So just a minute. Just a minute. Okay. So let's go to the next question. Okay. If you have any doubt, you can comment it. Okay. If you have any doubt, let me know in the comment section. And so let's solve this. This is also the same type of question. Um, 146 base x, okay, plus 313, sorry, base x minus 2 equals to 246 base 8, which you will get a equation that is x square plus 4x plus 6 plus 3 into x minus 2 whole square plus x minus 2 plus 3, which is equals to 2 into 8 square plus 4 into 8 plus 6. So this is a simple equation. X equals to 4x cannot be 4 because you have 4 here. So the base cannot be 4. X is greater than 4. Okay, you are talking about, I think, the previous question. Okay, that's because the number is 43 base x. So radix should be greater than all of the digits here. So it should be greater than 3 also, it should be greater than 4 also. So we take the maximum one and we assume get x should be at least greater than 4. That is the property of radix. Okay, so let's come to this one. It's a simple equation that I think you can solve. I don't have calculator here, so okay. So I think let me use this. X square plus 4x plus 6. Okay, 3 here, x minus 2 whole square. Okay, so hmm, so do one thing here. Let's do it. 2x and this will be 6x. Okay, plus 4, 3 fours are 12 plus x minus 2 plus 3, which is plus 1. Okay, 2 into 64, which is 128 plus 32 plus 6, which is 38. Okay, so you have 4x square plus 4x minus 6x plus x. So 5x minus x, that is minus x. Am I right or am I doing anything wrong here? So, hmm, plus 4x x minus 2 whole square. So you will get a minus here, minus 6x, and also here it is plus x and minus. Okay, it's okay. So let's do it. Minus x, and you have 6 here, it is 7 here, so you have plus 7 equals to, so plus 7 you can send it here, which will be 128 plus 31. Okay, so 4x square minus x minus 159 equals to 0. Okay, so I think you can solve it here. Okay, so like if you take 3 common, 3 is a 12 and it will be 3 5 3. Okay, wrong. I was also thinking something I'm missing there. Minus 6x. Okay, it will be plus, I think. Huh? Okay. Sorry. Yeah, yeah. It will be plus 12x. Yeah. Yeah, I was also thinking there is something that is missing. Yeah. 2 twos are 4 and 4 threes are 12. Yeah. Okay, fine. Thank you. So it will be minus. So 5, it will be plus 7x. Hmm. So plus 7x minus 159. I think every other thing was okay. 4 threes are 12. Okay, fine. Or it is 1 minus 19. 32. Okay, fine. It is 147. Mm-hmm. Yes. 147. Yes. So 112. You have 12 here, 6 here, and 1. If you send it 12, 18, 19, yeah. So you will have here as 19, and that is 147. Now you will have the solution for x, which may be 27, 21 and 7. Yeah. 21 into 7. 7 and 21. At 1 minute. Sorry. 4x plus 20 is 1. So 4x square plus minus 28x plus 21x minus 147. Sorry, 21, because we are dividing it by 7 and multiplying it here, so 28. Yes, so you have 4x x minus 7 plus 7 into, sorry, 28x, yeah, 21 into x minus 7. What's happening? X minus 7, okay, which is equals to 0. So again you have solution, that is x equals to 7 or 21 by 4 minus 21 by 4, which cannot be the solution. So your x equals to is 7. Okay, so this is a totally numerical type. um, this is also same type of question. You have to find the base r1 and r2. You can equal these two, you can equal these two, and you will find the value of r1 and r2 in these two equations. Okay, sorry, can you explain what you are saying, like arising, that means? Okay, I think you are talking about that plane. Okay, x equals to 7 in this position you are saying. Okay, this is the equation that you also can solve, like if you want me to write it here in a proper way, that is 4x plus 21 into x minus 7 equals to 0. Okay, so okay, so let's solve this. Okay, so first 235 base r1 equals to 565 base 10. Solve this. 2r1 square plus 3r1 plus 5 equals to, it is already given in base 10. Okay, so you don't have to do anything. 565, you can write it directly. Okay, so again you come here and solve this. Minus 560 equals to 0, and you have 2r square r1 square 560, so you can convert it into like 32 here, and this 30, 32 and 35. Okay, so plus 35 r1 minus 32 r1 minus 560 equals to 0. Okay, so take this as common, 2r1 from this and this, so you are getting r1 minus 16 plus take 35 common, you will get again r1 minus 16, which is equals to 0, and you have r1's value. Okay, let's write it total in full form, that is plus 35 and r1 minus 16, that is equals to 0, which results r1 equals to 16 or minus 35 by 2. Okay, so 16 is your answer because negative cannot be. Okay, base cannot be negative. So the same way I think you can also do for r2. So, okay, so can I go to the next question? Okay, okay, fine. So we have here, we are starting with data representation here. So data that we store in our memory, that can be unsigned number, that can be a signed number. Okay, unsigned number means there is no sign before the number, there is no positive and negative. Okay, we just consider it as a number. A signed number means there can be sign, there can be positive number, there can be negative number. Okay, so in unsigned number what we do, let's say, to convert a number, let's say the number is 12. So you just exactly convert the same number into binary. Okay, 0 1 2 3. Okay, this is 12, and you, to convert this you need only 4 bit. Okay, you need only 4 bit to convert this, you don't need any extra or bit. Okay, because there is no need for additional information, this is the whole information you have stored, there is no plus minus, you have to store this. Okay, the same way sign number is something different, because here you have to also store the sign, what is written here, plus or minus. So for that there are three methods that we will learn. First one is sign, it is normal, that is sign magnitude, also we say sign magnitude. Another one is one's complement and two's complement method. Okay, so let's go through one by one. First one is sign magnitude numbers. Okay, so what we do in sign magnitude, it is the simplest one. uh, hmm. So this is the simplest one. Let's say if we have the number as minus 12. Okay, how you will do, you will convert 12 into as it is unsigned number, that is 1100, and to represent this minus you will append another one here. So to convert it you need one extra bit, one extra bit. Okay, so if you have storage of n bit, so you can store only n bit. So what can be the value, what can be the minimum value and maximum value? Minimum value, just check, just consider, imagine this, you have total n bit storage, so one bit you have to give for sign. This will represent the sign, so this is one bit and you are left with n minus 1 bit. So using this you can represent 2 to the power n minus 1 numbers. So using, when you add 1 here you are getting the lowest number, that is minus 2 to the power n minus 1. 2, maximum number will come when you will put 0 here, that is plus 2 to the power n minus 1. This is your whole range of sign magnitude form. Okay, any other information, like one other information that you can note, for 0, for the number 0, minus 0 you will represent, like let's say you want to represent in 4 bit, it will be 1000, and plus 0, it has different same representation, sorry, like same number has different representation, that is 0000. Okay, this for sign magnitude has different representation for this one same numbers. Okay, okay, fine. So let's go to the next topic. Next, that is first complement form, where you write the number and you take this magnitude and you do first complement of this and then add sign. Okay, like for example, 12 is 1100. Okay, you take the first complement, that is 0011, and this is a negative number, you add 1. This is the whole process, okay? Like if it is plus, you add 0. The same way, and ranges also will be same, you can see. So if you have this total n bit number, you use this 1 bit for sign, and here in minus 1 bit for the value. Okay. Okay. Okay, so I'm just trying to do from basics, so that's why I am repeating this. Okay, so I'm taking this a little bit fast forward. Okay, so we will, so that we can solve more number of questions. Okay, two's complement. So in the two's complement, what you do, you take minus, let's say again, let's take any other number, it's a minus 8. You have the negative sign, so first you do two's complement. So minus 8, or it's a minus 5. 8 will be all zeros, 1 all zeros. So first take two's complement of, you can take two's complement of plus 5 like this. So you have 0, two's complement of 0, 1, 0, 1. This two's complement, you have to take two's complement of this, okay, which is equals to 1, 0, 1, 0 plus 1, which is equals to 1, 0, 1, 1. Okay, this is about minus 5 base 2. Okay, the same way you can do it for plus 5. Take 2's complement and you will just have 1. So that's just one thing here I have to say. If this is a number that is represented in 2's complement form, if you want to store the same number in 8-bit memory, how you will store it? So what you will do, you will extend the sign bit here to store the number. In general, what we do, like if your number is 111, we, if we want to represent it into 4-bit, we write it as 10111. No? But here, since it is a signed number, so you will extend the sign bit. So here sign bit is 1. So to store it into 8-bit, so you will extend 1 and 1011. This will be your number in 8-bit storage. Okay. So okay. So let's do it. We have to represent minus plus 15 and minus 15 in all three forms using 8-bit. Okay. So you have to use 8-bit. All three forms means first sign magnitude, sign magnitude. So just take the magnitude, convert it, and add plus 1. That is for plus it is 0, and for minus it is 1. Okay, so for 15 we know the converts, in binary it will be 1111. Okay, so it is, I am writing this for plus 15, and as a sign bit you will add 0, 0, 0, 0. Okay, so this is for, you have to add this as sign bit, and other 0 we are adding because we are said to convert it into a 8-bit number. Okay, the same way, if you have minus 15, you will have 1111, because sign bit is 1, and you have other all ones. Okay, so hmm. So this is 8-bit representation. Now comes to ones complement. So again take the ones complement of 15, which will be uh, again 1111. For positive number we don't do any complement. Okay, for, because this is a positive number, so we don't do any complement, and we just write for sign it is a 0. Okay, for negative number, so this is a positive number, it is same in all three representation. For negative number, what we will do, first we will complement, do first complement 0, 0, 0, 0, and keep all these as ones. This one represents sign bit, and this is the extension. because we have to represent it into 8 bit. Okay. Now comes to 2's complement form. Okay, so this is all base 2. Now in 2's complement also, the positive number will have no change. Uh, okay, this is as plus 15. But for negative number, you will add 1, 0 and 1 for negative number. Is it clear? Okay, fine. So this is a get previous year question. So let me know the answer. So what it is saying that you have a number that is 4-bit number, okay, and it is a 2's complement representation. This number, when it is stored in 8-bit, what will how it will be stored? Will you append zeros and font? You will append ones, x3 or x3 bar. Okay, this is a bar. Now, since this is a 2's complement representation, that means this is a signed number. Okay. So for a signed number, just we have discussed that you cannot append only zeros, you cannot append only ones. Okay, you have to extend the sign bit. So in this number, the MSB most significant bit is the sign number sign. So you have to extend that. That x3 will be repeated here. So C is the right answer here. Okay. Now, okay, this is a good question, and maybe you can learn a new concept here. So you are given a 16-bit signed integer. The 2's complement representation of p is given here. Okay. So what will be the 2's complement representation of 8 into p in hexadecimal in the same form? We have to write. Okay. Okay. So you are given in hexadecimal. You have to multiply it using 8, and then you have to write the hexadecimal form. Now you can do direct multiplication, which is not easier, like it will be more tougher. So you have to find out some any other way to do it. So the way is left shift and right shift. Okay, right shift. So what happens is that when you want to multiply, let's say you want to multiply 2 with a number 1011. Okay, if you want to multiply 2 with this number, instead of multiplying, what you can do, this is I'm talking about decimal. Okay, instead of multiplying directly, what you can do is that you can do left shift operation, which multiplies it by 2, that is 1001, and you append 10, so you have shifted the left side. Okay, so if you a number is x and you do r bit left shift, that implies a new number which is x into 2 to the power r. Okay, and the same way for right shift also, if you want to divide a number using 2, 1101, if you want to divide it using 2, so you will do right shift, which will result 110. So you are shifting this side, it is doing division. Okay, so right shift will result you divided by r. Okay, 2 to the power r. The same way, so let's now do it quickly. If 7b convert this number into binary, that is 1111 and 0, sorry, 1000 for 8, for 7011, for b it is 1001. Okay, So this is a number, so you have to do multiply it using 8, which is equals to 2 cubed. So you have to do 3 bit shift operation, left shift operation. Okay, but look at one thing, the number is 16 bit it is given, so you have to keep it in 16 bit. Okay, so you cannot increase the number of bits. Generally here, after left shift the number of bits increases. Okay, so here if number of bits increases, we will discard these. Okay, so if we do it here like 1 1, we are shifting, so these three number will be discarded. So 1100 0001 1110. Okay, 10, this three number is discarded, so this 4 and this 4. Okay, 1100, and you have another 000. This is your new number. Okay, after multiply. So now you can convert it here. It is C, it is 3. Okay, okay, here it is 1. So it is D, it is 8. Okay, it's in 16 base. Okay, okay. So if you have any doubt, you can tell it, you can comment it. Otherwise, let's go to the next question. Okay, so before the next question, let me talk about the test series. Possibly you have also know, get this time get Geeks for Geeks is coming with get test series, where you are getting 22 subjective tests and 10 full mock tests that is curated by IITians, and also you are getting short notes. Okay, that you can like revise it anywhere anytime, and we have pocket friendly test series for all India mocks, and I can see, I can assure you that you will find some very good questions. You will learn some very good concepts there in the test series. Okay, so yeah, in the description you can find, in the description there is a link is given for test series. Okay, you can go and check it out. Okay, fine. So let's come to binary code. Okay, so the binary code we are doing currently, that is a normal, like we are converting into some weighted code. It is called weighted code because like you have 1 1 1 0, and you are assigning some weight to each bit. Yeah? So you are assigning some weight to each bit. This is called weighted code. Okay, there are many more types of code. First comes is alphanumeric code, where you also represents alpha character, that is A to Z, small a to Z, and any special characters into some binary form. Some example is ASCII. Okay, and there are some numeric codes where weighted code is normal that we are using this. Also there is BCD. Okay, it is also called 8421 code, and you have non-weighted code, that is XS3 and gray code. Okay, so we will learn it one by one. So ASCII, you don't have anything to learn there, so let's start with BCD code. What you do in BCD code, that every digit in decimal converted into a 4 digit binary number. 4 digit binary number. Okay, so for example, like any zero, you will write it as 0001. So this is normal binary numbers. Okay, so when you have a mixed number, let's say 49, this base 10, you have to convert it into binary but in BCD code. How you will do it? You will convert 4 into a 4-digit number, that is 0100, and you will convert 9 into a binary number, that is 1001. Okay, so this is base 2 but in BCD. Okay, in BCD. So if you have in bit in decimal number, then you have foreign bits in BCD code. Okay, 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 fine. So then comes to access tree. As the name suggests, that you have the process is same, but the representation of each digit is different. Like in decimal, you have 0, and in binary, you are writing this as 0000. Okay, so instead of writing this, you will add more 3 to this number. So you will get excess 3, which is 0011 base 2. Okay, for 1 it is 0100 base 2. Okay, like this you will have your numbers. The same way, if any joint number you like come with like 10 base 10, sorry, base 10, to convert it into excess 3, you will write 1000, and for 0 it is 0011. This is excess 3. Okay, now here you can see each digit don't have any weight. Like in BCD also you had weight like 1, 2, 4, 8. Okay, but here you don't have any weight. So that's why it is comes under non-weighted codes. Okay. So now it is come to gray code. Okay, so in binary, possibly if you have done K-map, you have written there it is as numbers as 0001, then 11, then 10. Huh? So why we are writing like this? This is nothing but gray code sequence. Okay, why? This is also called unit distance code. Unit distance code. Okay, so let's a number in binary. Let's do it for 3 digit. Okay, and we will write the corresponding gray code. Okay, so for 00, let's do it for 2 digit first, then let me show how to extend it for 3 digit. So 011011. This is in binary, and in gray you write it as 11 and 10. Now every two sequential digit has numbers as only unit distance. So when you add 0 here, that is becoming 3 digit. So also add 0 here, and you will write here like 100101, the binary sequence. And here how you will write? You will mirror these numbers with 1. Okay, 110, 111, 101, and 100. Okay, so this is how you can convert binary number into a gray code. Okay, so let's go to some numericals. Okay, so here we will also learn a formula how you can do it. Okay, so let's do it for first. Let's go to binary to gray. It is 0, 1, 1, 0. It is given in binary. Okay, you have to convert it into a gray code. How you will do it? You will first copy the first digit as it is, then do XOR between them. 0, 1. XOR result is 1. So 1, 1 XOR result is 0. 1, 0 has XOR result as 1. Okay, this is in gray code. Okay, so if you take the reverse, if you have gray code, 1101. So if this process is clear to all, okay. So otherwise what we will do, we will again write it one as it is, and then we will XOR between these two. Okay, so 1 1 XOR with 0, then 0 0 XOR with 0, 0 1 XOR with 1. So you have 1001 base binary. Okay, so this was a gray code and we are converting it into a binary code. Okay, so yes. Now another topic from where maybe questions are coming this time, also previously 2 3 times question coming from this topic. So I wanted to cover this also. So let's cover it shortly. So you have IEEE 754 representation. Okay. So this is a standard representation that is actually used to store the number. Okay. This is some standard that is defined by IEEE that is used to store floating point representation. There is mainly two type of representation, that is single precision and double precision. In single precision, we store the number in 32 bit, where the first one bit is used for as a sign. Okay, and you have exponent bit as 8 bit. Okay, and you have at last mantissa with 23 bit. Okay, in single precision, if you sum all this, you will get 32 bit. In single precision, in double precision, what you have again 1 bit for sign, 11 bit for exponent, and 52 bit for mantissa. Okay, fine. So, and also there is a term that is called bias. Okay, how it is defined? It is defined as 2 to the power e minus 1 minus 1. Okay, so in the single precision, the bias is 1 2 to the power 8 minus 1, which is 127. And here is also bias is 2 to the power 10 minus 1, which is 1023. Okay, so in the IEEE there is something called special numbers. So there is some numbers which is specially defined and which cannot be like directly converted to decimal. You have to consider those number as special number. Which are those numbers? So when exponent has all zeros and mantissa has all zeros, then we call this number as plus 0. Okay, and also your sign is 0. Since sign is 0, you will add plus, and exponent and mantissa both are 0, so you will consider this as 0. When sign is 1 and mantissa and exponent both are 0, you will consider this as minus 0. These are some special number that is already defined, so you will not find any logic here. So here it is 0, and when all the exponent is 1, okay, all the exponent is 1 and mantissa is 0, it is called plus infinity. Okay, same way if it is 1, it is minus infinity. Okay, so when mantissa not equals to 0, there is something in mantissa, but exponent is all 1, then it is called NaN, that is not a number. Okay, when all exponent digits are 0 and m is not equals to 0, it is called denormalized number. Okay, d. So we will see what is denormalized number in detail. Denormalized number. Okay, and when e exponent is also not 0 1, and your mantissa is also equals to something, which is so at that time it is called normalized number. So we will see this in little bit details. Okay. So okay, fine. So generally, a number we consider it in the form as mantissa into base to the power exponent. We represent like this a number. Like any binary number, if you take like 1.01. Okay. So that number can be represented as 1.101 into 2, 2 to the power 1. When you multiply these two, you will shift this point by one digit to the right. Okay. You can consider this as our normal number, where we write like 12.34. We can write it as 1234 into 10 to the power 1. So any number can be converted into this form. Okay. So if there is an 1 here before the point, you say this as normalized number. Okay. Normalized number. There are some numbers which cannot accommodate in the mantissa. At that time, what you do, you let it go here, and you append zeros. You let it stay here 0, and you write it here like 0.1101 into 2 square. This is called denormalized. Okay. Last sign in table. Last sign. So it is normalized number. Okay, okay. This is not visible. Okay, fine. Okay. This is 0 1, and this is also 0 or 1. Anything can be in the sign bit. So I am writing in the, this is sign bit. Okay. It can be anything. Right? Okay. Okay, fine. So let's take a number. Let's say 1.1 into 2 to the power minus 126. Okay. So how we can represent this? So to represent this, we have to find values of three variables: s, m, and e. Let's say we want to do it in single precision. Okay. Single precision. So sign number. So since this is a positive number, okay, so simply we append 0 here. Mantissa is what is what is there, like after point what is present there, that is called mantissa, which is 1. So you cannot store just 1 because mantissa is of 7 bit, so 8 bit, so sorry, not 8 bit, that is 23 bit, so you have to append zeros here, and at last there will be 1. Okay. Like this, no, actually not, sorry for the mistake. So since this number comes after point, so you can append as many as 0 after 1. Okay. Not before. Okay. The same way, to represent exponent here, you have to add bias. Okay. So this is small e, we call it as small e, which is given as 1 minus 126. To get capital E, we add 127, that is the bias value, with e, you will get 1, that is represented here as exponent. Okay. And this is how single precision work. Same way, to go to double precision, just your mantissa will have more zeros and your exponent will have more bits. Nothing will be changed. Okay. Now there can be some numbers which is in this form, like let's say 1110.11 into 2 cube. Okay. Now you just cannot consider this as your mantissa. to get the mantis, you have to shift the point to the leftmost digit one after this one. Okay, so 1.11011 into, so you have shifted three digit, na, three digits. So multiply it to the power 6. Now you can do it in the same way. Sine is 0, mantissa is 11011, and your exponent is, you take 127, that is bias, okay, in single precision, okay, in the single precision, plus 6, which is equals to 133. So it will be converted into binary, okay. The base 2 of 133 will be your exponent, okay. So let's say another number, another example, let us consider, where you have 0.0000011 into 2 to the power minus 126 already, okay. Now look at here, if you shift these zeros to 1.1 into 2, so how much digit you have shifted? 1, 2, 3, 4, 5. So your number will be 131, isn't it? So if you add bias to it, so your E will be 127 minus 131, which is equals to 4 minus 4. So this cannot be your E. E is always positive. That's why we are adding the bias, so that our negative number gets cancelled. So this is the case. This is the case when you call this as denormalized number or overflow. Okay, overflow. What you do at that time? At that time, you keep the power in minus 126, and the whole data coming in the mantissa side, you store it into mantissa. Okay, let's write it here. Your mantissa now will be 0 0 0 0 0 1 1, then all zeros. Okay, your exponent will be all ones. Your exponent will be all ones, and sign bit will be obviously 1. Now when you will get fetch your number, since you are seeing all exponent as 1, you will understand this is a denormalized number. And when you will understand this is a denormalized number, you will not write 1.m. You will write 0.m. Okay. So after 0, so your number, when you fetch it from here, you will simply write 0.0000011 into 2 to the power minus 126. You don't convert this exponent directly now, because this is a denormalized number. This exponent will be always minus 126. That's how you can convert it directly. Okay, so this is one concept. Okay, and so so if you have taken notes, so let me just erase something so that I can write it here. Okay, okay, fine. So you can have explicit normalization or implicit. What is the difference? The same digit, like let's say 1.11 into 2 to the 2 cube. Okay, same number you can write it here like 1.1 into 2 to the power 4, and the same number you can write it here. Sorry, it is explicit normalization. Huh. Okay, so in the implicit mode you write it here, and in the implicit also you write it here, but In the explicit mode, you add the bias, and in the implicit mode, you add bias, sorry, with a 1, with a 1. So when it is comes to IEEE, we always do explicit normalization, okay? But if the question asks you to do it implicit, so you add one more. And in the implicit or normalization, there is no special number, okay? There is no special numbers, okay? So okay, fine. So that's all from this topic. So you have a contest, okay? You will find the link in the description. So you can go and attend the contest, okay? So you will find some like good questions there. So I would suggest you to go and attend the contest, and also as well with contest for the short notes and test series. Again, you can visit the description. You will have this here, okay? So if you have any confusion or any topic that you want me to say again, okay, so you can say that, okay. You have any confusion, any numerical or anything? Okay, overview. Okay, okay. The in summary, if I say about IEEE, okay, mainly you have two type of IEEE. In IEEE specific, I am saying, so you have two type of representation: single and double precision. Okay, in the single precision, you use 32-bit to represent one number. In double precision, you use 64-bit to represent one number. Okay. A second point is that sign bit, in both of the cases you use one bit for sign. That is 0 for positive number and 1 for negative number. Okay. Then you have exponent of 8-bit in single precision, but in double precision you have exponent of 11-bit, mantissa of 23-bit in single precision. In double precision it is 52-bit. Another term that is defined here in IEEE, that is called bias. What is bias? Bias is 2 to the power e minus 1 minus 1. What is e? E is the number of bits used to represent exponent. Okay, so that is 2 to the power 8 minus 1, which is 127 is the bias of single precision, and 1023 is the bias for double precision. Why this bias is used? Because the numbers we write here, it should be a positive number. Okay, so if you have a number, let's say 1.1 into 2 to the power minus 3, okay, in this case you can see this number, to repeat, to write down this number in the exponent, you have to consider this as signed number, na? So to get over this, instead of assuming this as signed number, what we do, we add this bias to the power. If the power is like minus 3, we don't store minus 3 here. We store e as minus 3 plus 127, which is equals to 124 in the exponent part. Okay, and the mantissa is same. After the first one, if the point is here, then all the digits coming here will be stored in mantissa. Okay, so exponent will store 124 and mantissa will store after point digit. The same way, if you come here, It is also same 1.1 into like 2 to the power minus 3. Now here your exponent will be what? 1023 minus 3, that is 1020, and your mantissa will be 100, all zeros. The total will be 52 bit, and 1020 will be represented in 11 bits. Now you can understand there is a limitation, na? Because you cannot represent, let's say in single precision, you cannot represent 1.1 into 2 to the power minus 130. So there is a limitation, because when you add minus 130 with 127, you are again getting a negative number as minus 3, which you don't want. So for that, you have an option of denormalized number in IEEE. What you do here, instead of writing like this, you add some more zeros, let's say 4, 3 zeros and 1, 1. So you have shifted 1, 2, 3, 4. So your number is now minus 126. Now you know you cannot add just a bias here and write down it into exponent. That's why you convert it into minus 126 power, and the whole number is written in the mantissa. Instead of looking for 1, you just write this number in mantissa, and in exponent you write all 1. And um, when you fetch this case will be here, like when this is 01, and sorry, sorry, normalized denormalized number, when all the exponent will be 0, you will store all zeros in the exponent, and your mantissa is not equal to 0, so this case will be considered, and you will know this is a denormalized number. And when you know this is a denormalized number, mm, where I have written that? Okay. So when you know this is a denormalized number, you write the number as 0.m into 2 to the power minus 126, and here you have sign bit. Okay, and if it is a normalized number, you write it as minus 1 to the power s into 1.m into 2 to the power the exponent you have there. And since uh, you have already added bias, so you will now negate the bias. Okay, so I think that is all from my side. um, okay, fine. So if you have any query, you can say, or I can end the session. Thank you all. Bye.